This chart plots the maximum displacement of a fixed aluminum beam as it is subjected to an increasing thermal load. Notice how the data smoothly arcs. The material displaces, but it finds a stable, measurable position at every temperature increment. Standard linear buckling theory cannot produce this. It assumes tiny deflections and perfectly proportional load to displacement. But at the critical buckling temperature, linear theory predicts mathematical failure. Stiffness evaluates to 0, and calculated displacement shoots straight up an asymptote to infinity. Real materials do not disappear into infinite space when they buckle. As a physical beam deflects out of its axis, the structural geometry shifts, and the material actively generates internal resistance to further bending. Our standard mathematical model lacks the mechanics to capture this physical self-reinforcement. To bridge the gap between that theoretical failure and the actual displacement curve, we have to formulate a nonlinear stiffness matrix and evaluate it using an iterative numerical solver. The necessary mathematical framework to correct this discrepancy was established by Theodor von Karman. When a structure bows significantly out of its original plane, standard linear strain equations break down because they do not account for the stretching of the neutral axis. The von Karman large deflection strain relation solves this. It takes the standard linear strain terms and adds a squared derivative of the transverse displacement. This expanded strain definition is then substituted directly into the standard volume integral for elastic energy. To find the state of equilibrium, we must obtain the mathematical variation of this total internal energy. Expanding this variation organically splits the internal energy into two distinct mathematical domains, a linear domain and a nonlinear domain. Standard buckling handles the linear term. Our mechanism for stability exists entirely inside the nonlinear block. Extracting and solving this nonlinear variation is the only way to quantify the variable physical resistance the beam generates as its shape deforms. The mathematical expansion of this nonlinear energy variation is dense. We simplify it using physical constraints, defining a uniform cross-section with a constant modulus of elasticity and measuring the z-axis from the centroid. This symmetry mathematically zeroes out asymmetric cross terms inside the integral. Second, for this specific fixed beam setup, we establish a boundary condition that forces all axial displacements to 0. This eliminates all terms dependent on the horizontal displacement, u, condensing the math significantly. We convert this continuous calculus integral into a discrete matrix format by applying standard beam interpolation functions. The result is a clean mathematical output, a second-order nonlinear matrix governed entirely by the nodal displacement vector, v. This N2 matrix is the exact numerical translation of structural stress stiffening. It is a calculated load resistance that scales precisely with physical deformation. We incorporate this matrix into the global equilibrium equation. Before the critical buckling load, the beam has 0 lateral displacement, so the N2 matrix evaluates to 0. But once applied load surpasses the threshold, deflection begins, and N2 activates to resist. This creates a computational deadlock. We need to solve for the displacement, v, but the stiffness matrix itself requires v to exist. You cannot process a direct algebraic matrix inversion when the stiffness depends on the unknown variable being solved for. To cross this mathematical gap, we employ the Newton-Lathston iterative method. We configure a residual function of forces to balance to 0. Its derivative builds the tangent stiffness matrix, adding a coefficient of 3. From an initial guess, the algorithm iteratively applies the inverted matrix, cyclically updating to converge on the exact displacement. We repeat this loop. When the calculated correction approaches 0, the sequence converges, isolating the structure's exact physical position at a specific post-buckled load. Which brings us back to the thermal displacement data for the aluminum beam. Every single coordinate tracked on this trajectory is the output of a successfully converged Newton-Raphson sequence. As the independent variable, the temperature, increases, the internal array logic responds dynamically. The matrix math is constantly calculating and updating behind the physical deflection, converging on a new equilibrium state for every fractional increase in load. The physical dimensions of the beam and the 71 gigapascal elasticity of the aluminum supplied the necessary rigid foundation to begin this dynamic calculation. The sequence moves directly from the physical geometry of the von Karman strain through the matrix reduction and into the numerical execution of the octave code. By integrating geometric nonlinearity into the system, we force the mathematical model to obey physical boundaries, translating a theoretical infinite failure into a calculated, verifiable engineering state.